Hello, everyone. Welcome to Inform's 2021 Yards and Terminal virtual session. My name is Jiaxi Zhao, a second-year PhD student with Road Tech at University of Illinois at Urbana-Champaign. Today, I'm going to present my ongoing research, Influence of Volume Variability in Railway Hump Classification Yards with AnyLogic Simulation. This research has four main objectives that ideally will be achieved sequentially. First of all, it is to evaluate some factors influencing hump yard capacity and performance that have never been studied fully with previous research. The next goal is to study the interaction between yards and mainline. Then, I plan to move forward to a network scope with multiple yards and eventually develop a high-level parametric yard model to benefit the railroad capacity and performance. This presentation will be focusing on stage 1, a single yard performance study. There are two areas of previous research relevant to the topics of this paper: evaluation of hump yard performance and capacity via simulation, and railway classification yards inbound traffic variability. Different types of manual methods, analytical methods, optimization methods, and simulation methods have been used for years. However, those studies usually focus on a specific yard. Therefore, a general parametric model is still needed. In terms of yard simulation software, early high-level ones lack the visualization of the yard operations. Besides, commercial softwares such as YardSim doesn't have the flexibility to modify the yard model. The uniqueness of each yard layout and operations even make it harder to build a model combining both high accuracy and flexibility. On the other hand, due to the flexible nature of North America freight railway operations, where no fixed timetables is used, and train sizes and departure times fluctuate according to the freight shipping demand, past researchers have studied the impact of variabilities on classification yards and terminals. In the most closely related paper, Dick and Nishio examined the property of classification yard to amplify or dampen volume variability by developing simulation experiments to study the relationship between schedule flexibility and volume variability. However, due to the limitations in the range of experimental setting available, their research had limited ability to investigate inbound volume variability according a range of yard operating patterns. And the level of volume variation achieved in their experiments failed to reflect observed levels of daily, weekly, or even seasonal throughput fluctuation present in actual railroad operations. This research proposes to expand upon and improve the previous research by quantifying the influence of a more representative amount of inbound volume variability on multiple yard performance metrics and comparing the train size distribution of arrivals and departures across a range of average traffic volume for different blocking patterns. This new approach is implemented with AnyLogic software, a multi-method simulation tool that supports discrete event simulation. It has a real package so that the customized layout of a yard can be imported from AutoCAD, which provides complete flexibility. And the visualization also helps to monitor the operation and make sure operation decisions are made correctly in each part of the yard. In addition, it is capable to build a mainline model in order to perform the network simulation. Here's a diagram of a representative inline yard layout I used in the model, where a 6-track receiving yard, 32-track classification bowl, and 6-track departing yard are located on the same line. And some of generic design parameters are also shown here. Here's a short video of simulation display that you can check on YouTube. And more details about the model, such as model validation, output metrics, can be found in the presentation last year. To investigate the research hypothesis, the experiment design starts with varying the inbound volume. The number of trains arriving in a day remain the same, and the initial schedule remains same inter-arrival time for all trains. The variables include daily throughput, daily volume variability, and individual train length variability. A baseline inbound volume is set as 60 cars per train, 80 cars per train, and 100 cars per train. Then a daily variation is added based on the baseline volume, which decides the average train length during the day. After that, the individual train length is adjusted by adding an individual train length variation to the daily volume. Here shows an example daily volume with 1280 cars per day, which is 80 cars per train on average with 10% daily variation. Hence, the daily volume fluctuates above and below the 1280 cars baseline. For instance, on day 100, 1,088 real cars are processed in the yard, resulting in an average of 68 car long train. Then look into this day. Despite that, the overall train length should be 80 cars per train on average. The actual train length fluctuates based on 68 cars per train instead, with a 10% individual train length variation. Implement the experiments with various throughput and volume variability. The simulation result in terms of average yard dwell time is shown here. The horizontal axle indicates different daily volume variation, while the patterns indicate the individual length variation level. The colors represent throughput from 960 cars per day to 1,600 cars per day. On top of this effect, increasing the individual train length variability and daily volume variability both create additional increases in yard dwell time. However, the extent of influence at low volume is negligible when the yard is relatively idle. In general, individual train length fluctuation and daily volume change have larger impacts on yard dwell time performance at high traffic volume. Of the two variability factors, when one is held constant and the other is varied, individual train length variation appears to have a stronger effect than daily volume variability. However, there appears to have an interaction effect as the effect of daily volume variability increases as train length variation increases. With higher levels of both types of inbound traffic variability, the combined compounding effect at larger traffic volumes is to cause much longer of average dwell time in the yard, indicating that the yard is reaching its maximum throughput capacity. Under the circumstance, with more inbound traffic variation, the capability of a yard to maintain a required level of service decreases, resulting in a reduction of the maximum traffic volume that the yard can process. Looking at train departure on-time ratio with the same experiment design, daily volume variation appears to have stronger effect on the yard performance in terms of OTO, opposite of that was observed for dwell time. Although the effects of daily volume variation and train length variation combine to produce the worst performance, there is a less obvious interaction effect, as both effects are more consistent for a given traffic volume. Based on the level of service, four performance groups can be classified. First, low variability with small or no variation, which results in ideal output, but is hard to achieve in reality. Followed by medium variability with some variation in either daily volume or individual train length, or some variation in both, which also maintains good yard performance. Larger variability starts to harm the yard with some or even higher variation in daily volume or individual train length. Lastly, extreme variability causes significant loss in the yard performance, which should be generally avoided in the practice. Three circumstances can be concluded combining the two metrics. First, when the yard is undersaturated with sufficient idle resource, a small amount of daily throughput and individual train length variability produce similar and negligible influence on yard performance. To some extent, the small amount of traffic variation offsets the randomness existing in the simulation model due to the diverse operating decisions. Therefore, under this situation, there is little performance benefit to stabilize inbound traffic. In contrast, some real cars even achieve shorter connection time, benefiting from the randomness. Second, when the volume is larger but does not exceed yard capacity, considerable inbound traffic variability begins to delay train departures, and hence the average yard connection time increases. In this case, the random long trains that occur due to the individual train variation or random high volume days due to daily throughput variation might cause temporary saturation in the subyard or even the whole terminal. A long train occupying the hump might cause unexpected queues in the receiving yard, and the long blocks exceeding their assigned track lengths need to take up extra tracks to store real cars, which further add to the complexity of pull-down operation. However, most of the extra resource need caused by the variabilities can be absorbed by the surplus capacity of the yard. Hence, the performance only shows a medium disturbance. Lastly, when the yard is at or very close to capacity, the yard is most vulnerable to traffic variability. Unlike the undersaturated situation, the extra resources required due to the random long trains and or the peak traffic days cannot be afforded anymore because there is little or no capacity surplus. Therefore, the yard level of service declines significantly and may even affect the performance of the mainline. After studying the throughput and the volume variation, the factor of block pattern is also introduced. Take the baseline 80 cars per train with no volume variation as example. There are 5 block patterns with various combination of short and block longs. The total number of blocks formed in yard vary from 16 to 32. For 16 blocks, each block contains 80 rail cars, which is called long block, and each outbound train hauls one long block during the departure. For 32 blocks, each block contains 40 rail cars, which is called short block, and each outbound train hauls 2 short blocks. For 20, 24, and 28 block scenarios, both short and long blocks are built in the yard, resulting in outbound trains either carry a single long block or 2 short blocks. Given the fixed 33 bolt tracks in the classification yard, the block-to-track assignment varies according to the block patterns. With more blocks built, more dedicated tracks are reserved for each block, resulting in less free tracks to store the rail cars that won't fit in the dedicated tracks. In addition, one track to store the rail cars that need to be rehumped later remains same for each block pattern. Implement the various block pattern as well as daily and individual train length variability to 80 cars per train volume. The common trend across all block scenarios is that both daily volume and individual train length deviation increases dwell time to the same degree, marginally at low to medium variability range and considerable at high variability. Another trend in this result is that as more blocks are formed in the yard, the longer rail cars dwell in the yard with any variability level. A possible surmise is that rail cars connecting to short blocks dwell longer in the classification yard compared with rail cars connecting to long blocks. To investigate this assumption, further examination is conducted. Here, average dwell time was calculated separately for rail cars belonging to different block types. Overall, rail cars connecting to short blocks require a longer time to process in the yard, resulting in a longer average dwell time for block patterns that have more short block trains. Dwell time in a yard for short blocks is longer no matter the volume variability scenario. However, long blocks are more sensitive to volume fluctuations as larger increases in dwell time can be observed for rail cars departing in long blocks as volume variation level increases. In order to answer the research question of does a hump classification yard amplify or dampen volume variability, the simulation output of inbound and outbound train size were compared for selected volume and volume flexibility scenarios. Given the yard throughput of 1280 rail cars per day and 16 outbound trains for every simulated scenario, the average inbound train size is 80 rail cars, and the average outbound train size is also constant at 80 rail cars. To determine how the yard propagates train length variability, distributions of inbound and outbound trains and all cumulative distributions were developed for the set of scenarios with daily volume variability ranging from 0% to 20%, and individual train size variability ranging from 0 to 20%. In a scenario with 0 daily volume variability and no individual train size variability, all inbound trains are consistently 80 rail cars in length, leading to a vertical line for the cumulative distribution. However, the outbound train length for this scenario shows more diversity and results in a bell-shaped curve for outbound train size distribution. The reason is that randomness of the other process within the yard simulation and multiple operating strategies. When variability increases, both inbound and outbound train size distribution spreads out to extremes and reveals a flatter bell-shaped curve. When the inbound traffic has low variation, the outbound train size distribution spreads and the yard exhibits the property of amplifying the inbound variability. In contrast, when the inbound traffic has high fluctuation, the outbound train size distribution becomes relatively centralized to average. And in this case, the classification yard exhibits the property of dampening volume variability. The overall conclusion is that the hump yard functions as a node that moderates mainline volume variability. In practice, as manifest trains travel in railway network and make different stops at classification yards, the train length is prone to be close to the main instead of extremely short or long trains, which will either cause operating difficulties or being incompatible with the cost-effective strategy. Then, the propagation of schedule variability is also investigated, starting with fixed schedule along with large volume variability. The cumulative distribution of train length is dampened from inbound to outbound. As of the offset from the schedule, given zero schedule offset for the inbound traffic, the variability is amplified from inbound to outbound. It also indicates that the volume variability can be transformed to departure time variation to some extent. Similarly, fix the volume variation and add deviation to the inbound arrival time. The volume variability is amplified from inbound to outbound, while the schedule variability is dampened from inbound to outbound. A similar surmise can be made that inbound schedule flexibility can also contribute to the outbound train length variability. Lastly, with both inbound volume and schedule variability, a dampening trend for both volume and schedule can be observed in the outbound traffic, although the trend of volume variability is negligible compared with that of schedule variability. Combining the three experiments, a conclusion can be made that the yard functions to moderate the variability, and the variation can be transformed and propagated between them. In summary, this paper used an original hump classification yard simulation model to conduct a novel experiment systematically investigating and quantifying the propagation and transformation of inbound to outbound variability. Increasing yard throughput variability damages the performance of railway classification yard by decreasing the ratio of outbound trains that depart on time and increasing the rail car dwell time in the yard. These effects are most apparent under higher traffic volumes as the yard's nearest capacity, because small amounts of variation in data volume and individual train size can still be handled efficiently when the yard is undersaturated. Based on the comparison of arriving and departing train size distributions and their performance, experiments result shows that rail cars connecting to short blocks have longer transit time in yard, while long blocks are more vulnerable to volume variability. The simulation also indicates that classification yards function to both moderate volume flexibility to medium values. Train arrivals with low volume and schedule flexibility and high volume and schedule flexibility both result in similar performance. The relationship and trends identified by this research can help understanding the role of hump yards in the railway network and encourage the railway to optimize the yard operation. However, future research should also focus on larger range of volume and schedule variability and attempt to study the interaction between multiple yards. Thank you for your attention, and special thanks to the support from Tyler Dick and Jordi Roscoe. Please feel free to make any comments or questions in the chat box, and have a good day.